Hello everyone, welcome to PST Lecture 1. Today we talk about power in a single and three-phase AC circuit. We'll talk about complex power and power transformer. So in a single-phase AC circuit, we start with the expression of the voltage and current. We assume that they are sinusoidal waveform and it's expressed by these formulas. Notice that theta V and theta I are the phase angles of the voltage and current. So if we multiply them together, we get the instantaneous power. And if we arrange the expression, what we get is the formula like this. If we take the average power over a cycle, what we get is the first terms, Vi cosine theta. Notice that the cosine and sine part will become zero after one cycle. This represents the real power consumed by the load. The second term here has the average value of 0, but it has its amplitude, and the amplitude here is called reactive power and is given by Vi sine theta. Notice that theta here is the difference in phase angle between V and I. So instead of multiplying things like that, we simplify things using complex number. So the complex power, or S, is given by this expression Vi conjugate. Notice that V and I here are complex number. So instead of using instantaneous value, we use complex number. We represent vectors like this. So if we do calculation with the complex number, what we get in the end is the same thing. S equal P plus JQ. J here represent imaginary part. So P represent the active power and Q represent the reactive power. The apparent power has the amplitude of the whole vector and it has the unit of volt ampere VA, while power has the unit of watt and Q has the unit of VAR or VA in reactive. So if we look at S as a vector, then its real power part is in horizontal direction like this, and the reactive power is in vertical. It has a phase angle theta, and cosine theta represent the power factor of a circuit. So is cosine theta, so the value will fall between 0 and 1. If the power factor is 0, then the power flow is entirely reactive. And if the power factor is 1, we have the case of unity power factor. That means the energy supplied by the source is consumed entirely by the load. The terms of power factor also come with the terms leading or lagging to show the sign of the phase angle. So here is the graph that explains leading and lagging power factor. So for a circuit with inductive character, for example, we have inductors, then it has positive Q, and we call in this case lagging power factor. It doesn't come from positive theta here, it comes from the fact that the current is lagging the voltage. On the other hand, if the circuit is capacitive, then we have a leading power factor or current lead voltage. And in that case, theta here becomes negative and we have negative Q. So what does power factor means? For example, To get 1 kilowatt of real power, if the power factor is unity or 1 kilovolt ampere of apparent power needs to be transferred. If we get a power factor of 0.5, for example, then we need 2 kilovolt ampere. Even worse, if we want to get 1 kilowatt of real power at 0.2 power factor, in total we need 5 kilovolt ampere of apparent power needs to be transferred via transmission line, and therefore we need to design the whole transmission line to be able to deal with 5 kilovolt ampere. So in order to reduce the capacity of our transmission line and power generation and cable transformers, we need to improve the power factor to near unity. So we need to bring the power factor closer to 1 by providing the correction. Power company usually install capacitor banks throughout the network as needed in parallel with loads, for example. So what we do, we take the original P and Q, and then we compute the Q new as follows. So this is the QO, which is quite large. We provide the QC in the opposite side. C represents the capacitor, and therefore the Q new is given by the QO minus QC here, and as a result the apparent power after correction is much smaller than the O value, and the power factor gets closer to 1. In a three-phase balanced circuit, we have three voltages. We have the same amplitude and is displaced by a phase angle of 120 degrees. The phase sequence is quite important in this case. So let's have a look. The voltage here is phase A, referred to neutral. And we have B phase and C phase. So if the sequence is A, B, C in clockwise, then we have positive sequence. And if it is counterclockwise, then we have negative sequence. Also, we have star or Y connection in three phase. In a star connection, the load is connected through a neutral point and to the ground like this. For a star connection, the line to phase voltage, we call it phase voltage. It is, for example, in our case, is 200 volt, and the line to line voltage will come from measuring between the two lines here is actually square root of 3 times higher than the phase voltage, and in our case, in our system, it is 400 volt. We also have delta connection like this. In this case, we connect the load between the line, and therefore the load is exposed to higher voltage, in this case 400 volt. As a result, the load current becomes smaller if we talk about the same power, and therefore the current in the line is 3 times higher than the load current. The power in three-phase balanced circuit can actually compute by multiplying the single phase with 3, given that the load conditions are balanced. If we look into the line-to-line voltage instead of line to neutral, then the formula becomes different. Instead of 3, we have square root of 3 because the line-to-line voltage is actually square root of 3 times higher than the phase voltage. Other than that, the cosine and sine remain the same. If we want to measure power in a three-phase system, we can use two wattmeter method. We can measure both active and reactive power in a three-phase system, balanced or unbalanced. We can also measure it using only two meters. The method is discussed in the lecture notes and also in any textbook. You can look into it and prepare for a lab session. The important part is that we understand what's going on and the importance of positive sequence and negative sequence. We will figure out that the positive sequence will have a different formula compared to negative sequence, and that is your homework. Next, we talk about power transformers, and they are very essential element in any power system. We have single phase and three phase transformers, and it can be used to step up the voltage or step down the voltage. These are the symbols that we can use for representing the power transformer. First, we talk about ideal transformer. An ideal transformer has zero resistance and lossless, or the input power will becomes the output power exactly the same. In this case, the turn ratio gives us the relation between the input voltage and the output voltage, as well as input current and output current. Here we refer them as primary and secondary side. Notice that for an increased voltage, we have a decreased current, and vice versa. In reality, it is not like that, and it is caused by the fact that we have resistive components inside and also inductive component. We also have to provide the transformer with magnetizing current, and also the core will have some loss, which can be represented by the RC here. So in a realistic transformer, we have this kind of equivalent circuit, and the voltage ratio of transformer of the input and output is not ideal anymore, but we assume that in the middle we have an ideal transformer, and the voltage ratio and current ratio here will be ideal. We can refer all the components to the primary side like this, and when we do this, the exchange formula is that we multiply the components with the turn ratio, and therefore the voltage will be multiplied up with the turn ratio, and the current will be divided. The components, on the other hand, will be converted using the square of the turn ratio, and after converting everything to primary side or secondary side, we can calculate the voltage and current according to the parameters, and then we can get the realistic value. For the three-phase transformer, it is actually made from single phase for each winding, and you can arrange them in delta or star or Y connection. So we have four cases here. The first case is Y delta connection. The second case is delta Y. Third one is delta delta, and the last one is Y connection. The difference is only that we have 3 or 4 inputs, and also the voltage they are different. They will be also different in the sense that we look into the sequence impedance later, but I will explain it later. Next, we talk about auto transformer. So the auto transformer is used to balance the output voltage, especially for the case that we need to stabilize the output. Next, we have a different kind of transformer called tap changing transformer. So in order to control the voltage at the output, um, we can change the tap here so that we have different output level according to the changing turn ratio. In general, the tap change transformer can provide us with a variation of plus minus 5 to plus minus 10% of the rated voltage. There are two types: off-load and on-load tap changing transformer. The off-load one requires us to physically disconnect everything, and then we can change the tap. The on-load allows us to change the voltage without switching off the load. In general, it operates under closed loop control and then maintains the output voltage in respect of the change in the load variation. So this is the end of the lecture 1. For homework, please prepare for lab 1 and go to the right session. Also, please practice tutorial 1, and I look forward to see you in the lab.